All right, so let's go and get started. Let me see if I've got everything sort of pulled up that I want. I think I do. Let me really quickly sort of overview what we talked about last time. And what I want to focus on are particularly the limit state checks. Okay, so if you recall, we looked at looking at cross-section proportion limits, and we did service limit state stuff and then strength limit state stuff last time to try and start assessing the capacity of a given girder. And one of the things that we sort of went through is we said, all right, if you look at a lot of these limits, a lot of this stuff is very easy to Excelify, quote unquote. You know, you can write a spreadsheet to compute a lot of this stuff pretty easily. So for instance, we looked at cross-section proportion limits and we said, all right, you know, if I've got a girder that has a 14 by 3/4 inch top flange, a 42 by 7/16 inch web, and a 16 by 1 1/4 bottom flange, I can go through and check all the web proportions and the flange proportions. It's not that difficult, right? It's pretty easy to write a spreadsheet and have it do all this math for you pretty basically. Okay. So, and in addition, we also did the service limit state. Now, we went through this and we found that the positive bending region was fine and all that. And the big thing I wanted to indicate was that, you know, how you do your stress checks, which is pretty basic, just M over S and applying your appropriate load combos. Was everybody okay with what we did last time? Anybody have any questions? Okay. You all have a design project, and I want to keep you moving forward on that design project. So I've developed a little homework assignment this week, and I know I still haven't gotten homework 2B to you. Just, you know, stuff piles up and whatnot, but I will get to it, I promise. I've developed a homework tonight that I want to keep you moving towards that project. So I want you to develop a small little or series of Excel sheets that will compute a lot of these limits that we talked about last time and the limits we're going to talk about tonight for a simply supported bridge. So for instance, cross-section proportion limits, that's pretty straightforward. The service 2 limit state check, well, think, if it's simply supported, where do I need to do the stress check? I just do it at midspan, right? Obviously, that's going to be where the largest stresses are. Now, composite flexural capacity, we talked about that last time. These 3 bullets we're going to talk about tonight, okay? I think you're going to find that all in all, this is pretty straightforward. So I've got a handout on that if you want. And I've got to admit a little bit of, I don't know, whatever you want to call it. Maybe it was a mistake on my part, but I'll be honest, the whole submitting stuff on MU Online, I thought that was going to be a little easier to deal with. Well, no, it's actually a little more difficult. It'd probably be a lot easier to just email me your assignments instead of doing it on MU Online. The grading process is a little tougher. So for this, I'm just going to have you all email me the assignment. Is that all right? All right. And I wanted to do this because I want to keep you moving forward on your project. The last thing I want to have happen is, you know, it's a week before the project's due and you're scrambling to do 80 billion Excel sheets and whatnot. So I wanted to give you an assignment that's, you know, relevant to what we're doing, but at the same time we'll keep you moving forward. All right, sound good? I mean, the ultimate goal with your project is that you're going to have this big spreadsheet that, based on, you know, some flange sizes or some web depths and whatnot, you should be able to compute everything, you know, your section properties, your distribution factors, your plastic moment, your yield moment, your cross-section proportion limits. You should be able to do everything. And you should be able to just tweak the dimensions to ensure that the bridge is satisfactory. That's sort of the whole point. So I know the spreadsheets will get a little big, but the idea is to build it a little bit at a time. All right. Any questions? Now, some of this stuff is going to be new, or you're not going to be aware of, like the non-composite flexural capacity and all of that. So, you know, I'm aware of that. We're going to get to that tonight. Okay, let me get the sign-in sheet passed around, which, by the way, I realized as we were leaving last time, I don't think I actually gave you all the handout of your project last time. It's posted on Blackboard, but I don't think I gave you all the handout. So here's this. Here's that. Which, did everybody see on Blackboard? I put an entry in the grade column, but it says something like project ID. Did everybody see that? That's your ID number corresponding to your bridge. So does everybody's match? I don't know if everybody saw that. Did it? Hold on. Did everybody get homework 4, or did I miss one? I got one extra. Oh. 4? You got it? Okay. Maybe I just printed one extra or something. I'm not sure. Okay. All right. So, everybody good? Okay. All right. So, tonight, what we're going to do is continue on with our discussion of flexural capacity. And what I want to really hammer in on tonight is non-composite strength. Arguably, the composite capacity stuff is pretty simple. I mean, once you determine MP, it's either MP or it's that linear fit off of MP, and that's all there is to it. The non-composite stuff is a little more involved. Now, has everybody in here had a course in steel design? Okay. If you have had steel design, you're going to find a lot of the formulas that we're going to discuss tonight are going to be somewhat familiar. They're not going to be exactly the same, but you're going to find that there's some striking similarities between what we do for steel bridges and what we did for steel buildings. Okay? I'm also going to hand you out this series of flowcharts. I'm just killing trees today, aren't I? I think that's enough. There's that. What's up? Oh, no problem. There's that. There's that. And there's that. Okay. All right, so everybody should have homework 4. You should have a handout on your design project. You should have the slide packet for tonight, and you should have a thing that says Appendix C on it. Does everybody have that? Okay. All right. So let's go ahead and talk about this a little bit. One of the things I tried to hammer in, not last time, I think it was the time before, is this idea of the differences between the behavior of a beam and the behavior of a plate girder. And I know I presented a lot of theory and differential equations. I know probably a lot of the ideas it was like a lot of it all at once. And I'm aware of that. I wanted to sort of let that stuff seep in a little bit so that when we actually start digging into the specification, you'll go, oh, okay, I kind of see where you're going with this. So what we're going to do is talk a little bit more directly about the specification. So you all have 610. We'll probably flip back and forth between that a little bit, but I want to sort of take it one step at a time, and hopefully you'll recognize, you know what, it's not that bad. Okay, so it starts off with section 610.6, which is just the broad, hey, here it is for the strength limit state. It defines the difference between what is a beam in the spec and what is a plate girder in the spec. Plate girders are governed by 610.8, and beams are governed by Appendix A. You'll find that a lot of the equations are very similar, and in all actuality, Appendix A is optional. You don't have to use it technically. My advice and the advice of any steel bridge engineer is that if you can use Appendix A, use it. Okay? It fits the behavior better, and it more often than not results in a higher capacity. And if all you have to do is do a little bit of extra math and you can save the fabricator and the owner some money, do it. Okay? So, you know, that's just sort of the philosophy. Now, one of the things that I want to illustrate right before we get into this is that no matter what, for bending, our resistance factor phi is 1. So it makes life a little easier. Everybody good? All right. Now, I've got a lot of equations for you tonight. Okay? I'm going to tell you right off the bat. I've got a lot of equations that are long and nasty. Okay? But I want to enhance a little bit of calm with a lot of these equations by saying that everything that we're going to do tonight is plug and chug. Okay? Like, I look at this L sub R equation, and I know it's nasty and it looks horrible. But in the end, You just plug and chug and you get the answer, okay? It's pretty straightforward, okay? And we're going to do an example tonight that when you're setting up your spreadsheet, it'll give you an idea that, okay, I plug these values in, this is the answer that I should get. So don't let the magnitude of these equations scare you. I know they're long, but it's just add, subtract, multiply, and divide, and the occasional square root, okay? Sound good? All right. Another thing that I want to illustrate is the specification itself can be a little nasty, okay? I know that, you know, you're sitting here following sections 10, 6, subsection C, and da-da-da-da-da. I know that that can seem a little daunting. So what I provided you is an appendix in the spec. This is Appendix C. That appendix has a whole host of flow charts in it that you can literally just follow for design, you know. Do I have a discretely braced compression flange? Yes. If so, calculate this. Is this condition met? No. Then this is what I do. You know, you can pretty much just follow it through. So if the spec is a little confusing and you're having a hard time following it, that's what this is for. Okay? Is everybody okay with this? Any questions? All right. All right. Another point I want to make is in terms of the format of what it is that we're going to see. When we're looking at compact sections, and what I mean by compact is I'm talking about girders that are quote-unquote stocky, you know, sort of thick flanges, thick webs. That's really the simplest way I can describe it. Whether a girder is compact, non-compact, or slender, or what have you, is a function of the width to thickness ratios of each element, okay? But the long and short of it is, if you have a girder that's fairly stocky, what you're going to find is that the limits in the spec are written in terms of moment. You know, phi mn has to be greater than or equal to mu, right? Make sense? If you have a more slender type element or a non-compact element, they're going to be written in terms of stress. Not the moment capacity, but the stress capacity. Instead of phi mn having to be greater than or equal to mu, we're saying phi fn has to be greater than some major axis bending stress. All right, does that make sense? So if I start hopping back and forth between moments and stresses, this is why, okay? The way the spec is written out, if you're dealing with a plate girder section, we treat the compression flange and the tension flange as sort of two independent objects. So we just look at the stresses on the top and the stresses on the bottom, or what have you. But if that girder is really stocky and compact, we can look at the whole girder as one cohesive unit. And that's the difference between beam behavior and plate girder behavior. Does that make sense? Everybody okay with that? All right. Now, let's go into this a little bit. So some of this is going to be pretty familiar because we did this last time. So let's start off looking at flexural resistance. Now, the first thing I'm looking at is flexural resistance of a composite girder, okay? So this is in section 610.7. So you all have 610. I want you to open that, and I want you to turn to that. So let's see. I'll even get on the right page. Okay. So section, I'm on page 6-139, okay? Everybody see that? Okay. So 6-139. If you go down to the bottom, we see, all right, 610.7, flexural resistance composite sections. Now look right here. It says for compact sections, this is the limit that you're meeting. Again, compact, we're talking about beams, about stocky sections. If you go forward a little bit and you look at non-compact sections, like right here, you'll see it's written in terms of stresses, not moments. All right? Make sense? Okay. Now, if I go back to the presentation, I say, all right, if we're looking at composite girders, we have to first determine whether or not that girder is in fact compact, if it's a stocky shape, okay? To determine whether or not a section is compact, we got to meet three limits, which is earlier in the spec in 610.6. The first one is that the yield stress of the flanges has to be less than or equal to 70 KSI. So I guess if I wanted to be diligent, I would say this better be FYF, FY the flanges. So if you want to write that in, that's all right, although I don't think that's the biggest deal in the world. Okay, so you have to meet this limit. You have to meet the limit of your web slenderness being less than or equal to 150, which we've already checked that, right? We're looking at that for our cross-section proportion limits. And we have to meet the following limit. 2 d sub Cp over Tw has to be less than or equal to all that. Remember d sub Cp, that's how much web is in compression at the plastic moment, okay? Does that make sense? And remember, we looked at our previous girder, and in the composite state, we found that d sub Cp was 0 because all of the web was in tension. Everybody remember that? So this was pretty straightforward, all right? Everybody good? If you have a composite section, here's your capacity, right? Remember, it was either MP or it was MP times this 1.07 minus 0.7 dP over dt. Everybody remember that? Now, one thing I didn't mention is that this value, whatever you calculate, you can't use a value larger than 1.3 times the yield moment. And the reason why is if that value gets too large, you start shifting moments in the wrong direction when you use moment redistribution. So that's really the main reason for that limit. But usually, in most cases, you shouldn't be broaching that anyways. You should be pretty straightforward. All right. Everybody good? Now that is your capacity if you're looking at a compact section. If you're looking at a non-compact section, we're not calculating moment capacity, we're calculating stress capacity of each flange. And the long and short of it is, for instance, the nominal capacity of the tension flange is essentially Fy, which I guess that's a little bit of a typo. I'm probably going to have one or two. That should be Fy of the tension flange. Sorry about that. I'm allowed a couple mistakes. All right. For the compression flange, it's essentially the same thing. Now, why am I multiplying it by RH? Remember, that's that hybrid factor. That's if you've got a girder that has different yield stresses on different flanges. You know, you might have a 50 KSI top flange or a 70 KSI bottom flange or something like that. Most cases, if you've got a homogeneous girder, if you've got the same grade of steel, then RH is 1. Okay? Now, RB is a web load shedding factor, and it has to do with the post-buckling capacity of the web you know, after it's undergone a type of bend buckling. In most cases, that value is going to be 1. If not, it's pretty straightforward. It's a pretty plug-and-chug calc, and we can look at that later. That's going to become maybe a little more critical next time when we look at constructability. I might go into that in a little more detail then. All right, but for more often than not, that's going to be 1, and it's going to be pretty straightforward. Everybody good? Okay. All right. Now, we didn't do this last time, but it's a pretty straightforward check. This is a ductility check. Okay. In other words, it's a pretty straightforward check, and all it says is that the ratio of dP and dt has to be less than or equal to 0.42. So if you remember dP and dt, they show up in this previous equation before. dP is the distance from the way top of the section to where the P and A is, and then d sub t, that's the total depth. That ratio has to be less than or equal to 0.42. And that just comes from a lot of testing and data observation that says when that ratio is met, you have sufficient ductility. Which, if you recall, ductility was something the spec wanted to deal with, you know, at the very beginning. Remember, they included these ADA factors for ductility and redundancy and operational importance, and they put them in there as placeholders. Well, they really are placeholders because, yeah, at least when it comes to the steel section of the spec, they handled ductility a little more directly. So again, just another, you know, point that those values are pretty meaningless. Everybody good? Okay. What I'm going to do is I'm just going to go through the spec and make sure you're seeing where I got all of this stuff. So, for instance, I'm in 610.7, composite sections in positive flexure, and here we go. the nominal resistance, flexural resistance of the section shall be taken as, if dP is less than or equal to 1/10 of dt, here's Mn. It's just a plastic moment. Otherwise, here's your capacity. So you see where I'm getting that? All right. We go through and define all these. I mean, let's read. dP, distance from the top of the concrete deck to the neutral axis of the composite section at the plastic moment. Pretty straightforward. d sub t, total depth of the composite section. This is that limit I was mentioning earlier, that the nominal moment capacity has to be less than or equal to 1.3 times the yield moment. Sound good? Let me see. If you're dealing with a non-composite or a non-compact section, your nominal capacity is RB, RH, FYC, or for the tension flange, RH times FY. The reason why the RB is not on the tension flange is because RB is a quantity related to the section stability. We're not worried about things in tension buckling. You know what I mean? Things in compression buckle, so we don't have to worry about it. Last, we've got our ductility requirement that dP has to be less than or equal to 0.42 dt. All right? I want to make sure you're seeing where I'm getting a lot of this stuff. Okay? Everybody following with me and everybody okay with this? Okay. All right. Now, let's look at a non-composite section. Okay, so the first step is to classify whether or not we're dealing with a plate girder or we're dealing with a beam. Now, I've got some snippets out of the spec. I'm in 610.6, so if you're on 610.7, we're probably going a few pages back. But if you go to 610.6, we have composite sections in negative flexure and non-composite sections. So I guess maybe I should clear that up a little bit. If you have a composite beam, but it's in negative bending, what type of stresses is the concrete seeing? Is it seeing compression or is it seeing tension? Tension, right? And concrete is a material that doesn't respond very well to tension, right? So if we're looking at ultimate capacity, we basically just say that concrete doesn't do much at all, okay? So, excuse me. So the long and short of it is when we're dealing with the composite sections in negative flexure or non-composite sections, we deal with them the same way. And it starts off by assessing whether or not we're dealing with a beam or a plate girder. Okay, so first off, sections in all kinked, continuous, or horizontally curved steel girder bridges shall be proportioned according to 610.8. So even if you've got a really stocky section, if you've got a curved bridge, sorry, you can't use Appendix A, okay? That's just the section being a little conservative. You got to keep in mind, anytime you have horizontal curvature, you don't have just major axis bending. You've got that twisting effect on the girder. And that's going to bump your stress level up a little bit in it. So we say, you know what? Let's just hold off a little bit and say we got to deal with this as a plate girder. And keep in mind that is dealing with the capacity conservatively. If you want to, I guess a simple way of looking at it, plate girders are essentially limited to their yield moment, and beams are limited to their plastic moment. So if you classify a section as a beam, you're saying you can squeak out a little more capacity out of it, okay? So, if you fall back to 610.8, you're being conservative, okay? Does that make sense? That's a really simplified way of looking at it, but it's not too inaccurate, okay? Everybody good? All right. So what else determines whether or not we're dealing with a beam or a plate girder? Okay, sections in straight bridges whose supports are normal or skewed not more than 20 degrees from the normal. So if you have a skew on your structure that's 20 degrees or less, you can classify it as a beam. Any more, you got to go with a plate girder. What else? Your yield strength has to be less than or equal to 70 KSI. We have the following Webb slenderness limit. 2d sub c over tw has to be less than or equal to that. Again, pretty plug and chug. And your flanges have to satisfy the following ratio. So IYC over IYT has to be greater than or equal to 0.3, which you should be familiar with what these sections are, IYC and IYT, because we did that for our proportion limits. Sound good? So if you meet all of this, you're a beam, and you get to use Appendix A. Otherwise, you got to fall back on 610.8. All right? Now, a couple things. Regardless of whether or not we're using 610.8 or whether we're using Appendix A, we have to determine three capacities, okay? We have to determine the capacity of the tension flange, and we limit that to its yield capacity. So I can actually answer that pretty easily. For if you're dealing with 610.8, it's just the yield stress times the hybrid factor. If you're dealing with Appendix A, it's the yield moment times this term RPT, and we'll define what RPT here is in a little bit. But that's it. Pretty straightforward. Okay? For the compression flange, we have two limits we got to look at. We've got lateral torsional buckling, and remember that's when the whole flange wants to kick out and twist a little bit, right? That's lateral torsional. Flange local buckling is when that flange wants to crinkle and buckle on its own. Remember that? Remember the difference between local buckling and global buckling when the flange wants to buckle by itself instead of the whole thing wanting to kick out? Remember that? That's the difference, okay? Now, keep in mind, if the girder is compact, we're looking at moment capacity. If it's non-compact, we're looking at stress capacity. Sound good? Now, if you've had steel, that should be familiar, right? If you've had steel design, you should remember a graph that looks something about like this when you looked at beams, okay? If you recall, when we look at beams in steel design, we define our LTB curve or our buckling curve to look something about like this. So this is region 1, which we define as the full yielding. So if you're talking about beam capacity, this would be MP. Remember, you got that linear fit between MP and MR, and this is our elastic LTB. Does everybody remember that from steel design? It might have been a while, but I know that you've dealt with it. This right here, remember we can shift the curve up a little bit with our moment gradient modifier, but I don't care what's going on, we still got to cap that value off at MP. Sound good? Now, the nice thing is, whether we're dealing with lateral torsional buckling or flange local buckling, it's still the same model, okay? It's still the same thing, okay? It still follows these three regions, and everything's all good, okay? I promise you're going to see a pattern that goes along that's pretty familiar, or should be pretty familiar, and it's pretty straightforward. All right, so let's start off with 610.8. Now, if you recall, 610.8, we're dealing with plate girder sections, okay? So these are the sections that are a little flimsier, okay? So everything you're going to see is listed in terms of stresses, not moments, okay? Sound good? All right. Okay, so the first thing we got to do is flange local buckling. Okay, now here's how this works. If we want to determine the flange local buckling capacity of a section, we need to start off with a few values. We got to determine a flange slenderness, which you should know how to compute from your cross-section proportion limits. And we need to determine these two anchor points, lambda sub PF and lambda sub RF, okay? Which are basically, if you want to know, those are these two terms right here on our curve, just where this point is and where that point is. Because basically what we've got to do is we've got to say, all right, here are our anchor points for our curve. Here is our actual flange slenderness value. Where do we fit? Are we in region 1? Are we in region 2? What have you. All right, sound good? Now, the last thing we have to compute is this term F sub YR. Now, F sub YR stands for a reduced yield stress due to residual stresses, okay? When you weld pieces together, you take a top flange and you weld it to a web, you're introducing a heck of a lot of heat into that section, right? Now, when that section cools down, maybe it doesn't cool down at the same rate. Maybe the outstanding elements cool faster than the flange and the web junction. Well, what happens is, just because of the fact that things cool at different rates, you can lock in residual stresses into your section. The same thing happens with like a W30 by 90 when it comes out of the steel mill. The flange tips in the center of the web, it cools faster than that junction where the flange and the web meet. So you lock in stresses right when you buy it from the mill. There's already stress inside that section. When we look at buckling capacity, we have to reduce our yield stress a little bit to account for those locked in stresses. Now, usually we assume that to be 0.7 Fy. And I know if you took me for steel design, I sort of hammered that into you. But because we're dealing with a plate girder, and we've got, we might have a 50 KSI top flange and a 70 KSI bottom flange and all this, the formula is a little more intricate. It's a little more complicated. But all in all, it is plug and chug. All right? Sound good? Okay. You'll find that if all of these yield stresses are equal, this comes out to be 0.7 Fy. So it's pretty straightforward. Now, once you calculate all this, it's simple. Remember I said there were 3 regions? Well, the spec doesn't allow slender flanges, so you don't have a region 3. So here it is. If you're in region 1, here's your capacity. If you're in region 2, here's your capacity. And how do you determine that? Whether your slenderness is less than lambda sub PF or whether it's greater than lambda sub PF. And that's it. That's all there is to it. I know this equation looks nasty, but again, it's just plug and chug. That's it. You know all of this stuff going into it. You know the yield stress. You've already computed all these slenderness values. You know your hybrid factor. That's usually 1. You know your F sub YR. It's plug and chug. That's it. I know it's nasty, but that's all there is to it. Sound good? Now, for lateral torsional buckling, you got to do something pretty similar. You've got to compute anchor points as well. You've got to have an L sub P and an L sub R, which, as you see right here, again, pretty plug and chug. Now, you're also going to need a couple other things, which we're going to talk about later, your unbraced length, and you're going to need this term C sub B. I would argue of all of the quantities that we're going to compute for everything associated with tonight, the one that's the toughest to get right is that right there. Okay? That's the one that's going to give you some headache, which is why I've posted something that'll help you out with that a little bit tonight. Sound good? All right. Ultimately, I think it's pretty straightforward, but it's what I've found can cause some confusion. So I decided to make it a little easier on you. Sound good? All right. All right, so what are you going to need for LTB? You're going to need your unbraced length, which is your spacing between your cross frames, however far apart they are. Your moment gradient modifier, which we'll talk about later. You're going to need LP and LR, which is this. You're going to need your reduced yield stress, which is the same thing you calculated before. You're going to need a radius of gyration, which for LTB, which is pretty plug and chug. If you recall, when we look at plate girders, we look at that top flange and then a third of that web depth. So that's just the radius of gyration of that T shape. And you're also going to need the depth of the web and compression, which if you're looking at a non-composite shape, just use the centroid. Pretty straightforward. Sound good? Okay. Once you get that, it's pretty plug and chug. Now, these equations might not look familiar right now, but when we look at Appendix A, some of this stuff is probably going to look very familiar. Okay? Now, we're looking at lateral torsional buckling, so we've got 3 regions. We've got a constant capacity in region 1, a linear fit in region 2. And if you look, a lot of these equations, they look very similar. A lot of the calculations are going to be very similar. Here's the local buckling check. Here's the lateral torsional buckling check. These equations look pretty similar, don't they? Now, for region 3, we've got this hyperbola. We calculate F sub CR. Again, very plug and chug. I know the equations look long, but the long and short of it is it's all plug and chug. Sound good? All right. Now, that's 610A. Again, I want to go through the spec and make sure you're seeing where I get all of this. So I'm in the spec, and if I go to, if I start off at 6-146, you can see where a lot of this stuff's coming from. So, local buckling resistance. Take a look at it. The local buckling resistance of the compression flange shall be as follows. If lambda is less than that lambda sub PF, there's your capacity. Otherwise, there's your capacity, right? I didn't just make a lot of this up. A lot of it just came directly from the spec, okay? And each one of these values that go into this expression are referenced right below it. You know, what is lambda sub F? It's the slenderness of the flange. What's lambda sub P and lambda sub R? Those are your anchor points, and so on and so forth. Here's your lateral torsional buckling capacity. Okay? Everybody okay with this? All right. Does anybody have any questions? Because I know I'm throwing a lot of formulas and equations at you tonight. The last thing I want to do is I don't want this to happen. I don't want that to happen. Everybody good? Don't worry. We're going to exercise a lot of this, okay? Don't worry. Everybody good? Okay. Now, did I give you all Appendix A? I think I gave you all that, right? Okay. All right. Appendix A is a little funkier. A lot of the calculations are very similar. Maybe the best way of saying it, they're just a tad more involved. Okay? Now, one of the things about Appendix A is that Appendix A deals in moments. It does not deal in stresses. Okay? So all your capacities are going to be Mn, not some F sub n. Okay? Make sense? Now, again, I know the equations might look more complicated, and you might think, well, if I'm an engineer and I have the option of using formulas this big or using formulas this big, why would I use formulas this big? Why don't I just do that? I'm telling you, if you use Appendix A, you're going to squeak out more capacity out of your girder. And if you can squeak out more capacity out of your girder in a design phase, you can make that girder smaller, which is going to save on money, okay? Make sense? So if all it took was a little bit of an extra formula, use it, you know? Save money, okay? Sound good? All right. Now, one of the things I will point out, though, is while the formula might turn from this to this, they're still going to look very familiar, and that was by design. They wanted the spec to be as familiar as much as possible. All right. Sound good? Now, the first step in using Appendix A is to compute what are called web plastification factors. And do you remember when I said that for 610-8, that's basically limiting you to the yield moment, but Appendix A, you were able to get theoretically to MP? You remember me saying that? Well, these web plastification factors are essentially a measure of how much higher you can get above MY. Okay? That's really what they are. All right. Sound good? Now, for web classification factors, we're going to need very similar starting values. Now, we're talking about web classification factors, so we're going to need slenderness values associated with the web. Okay, so we're going to need a lambda sub W instead of a lambda sub F. We're going to need anchor points, lambda sub PW and lambda sub RW. Now, they're a little more involved, but again, plug and chug. We're going to need our hybrid girder factor, which we should know. We're going to need the depth of web and compression at the elastic range, where we just use the centroid. But we're also going to need the depth of web and compression at MP. Okay? Now, one of the things I want to indicate, remember that MP example that we did last time where we looked at the plastic force and the slab and then compression flange and web? Well, we're looking at the non-composite capacity. So I know it sucks, but you're going to have to do another MP calc where that, and that are all zero. Okay? Make sense? All right. Now, you're going to need these anchor points. Here's the anchor points. I know the math is a little more hairy. Again, plug and chug. Now, one point I do want to make. You recall when you calculate yield moments, you can get a yield moment for the compression flange and a yield moment for the tension flange. So you might see this term and you might go, well, which one do I use? Anytime you see MY, use the smaller. Okay? Sound good? Don't worry. We'll go through this in detail. All right. Once you calculate those values, RPC and RPT are pretty plug and chug. So if your slenderness limit is less than your anchor point, there you go. Otherwise, there you go. The formulas are very similar for RPC and RPT. All right. Everybody good? Okay. Now we can start calculating capacity. For flange local buckling, we're going to need flange slenderness and flange anchor points. We're also going to need a flange buckling coefficient, which is pretty straightforward to calculate. If you're looking at a rolled section like a W shape, you always take this to be 0.76. You have to take it between a range if you've got a plate girder. Now, you also have to calculate a reduced yield stress, which I do want to point out the formula is a tad different because you're looking at moments, not stresses. The formula's slightly tweaked a little bit in this center range. Now, for flange local buckling, again, the spec still doesn't allow slender flanges, so there's only two regions. It's either MY or MY times your web classification factor, or it's that linear fit off of that. And it's determined by whether or not your flange slenderness is less than or equal to the following value. And that's it. Okay? For lateral torsional buckling, again, similar steps. We're going to need an unbraced length. We're also going to need CB. Okay? We're going to need our anchor points. We're going to need our reduced yield stress, a radius of gyration, as follows. Now, here's some of the formulas that wouldn't fit on that slide. Again, they look nasty, but it's plug and shut. All right. And here's your capacity. Now, I've got to believe that formula looks at least a tad familiar for you folks that took steel design. That at least looks something familiar if you took steel? Okay, all right. I see some folks shaking their heads. Yeah, I remember that. Good, good. All right. You can think of this as MP, the linear fit off of MP, or your elastic LTB. It's not quite MP, but in many cases, you're able to get to that. So far, so good. Okay. I wanted to be convenient, so I wanted to go ahead and throw this back into the mix. So here's the dimensions for this example that we've been looking at for the past 10 weeks. I know it's probably getting a little tiring. When we do shear next time, I actually have a different example for you. I know. I can see you all are having a hard time containing your excitement over the whole thing. That was a joke, not a very funny one. All right, so here's our bridge cross-section, same deal as before. And here's our girder, same deal as before. Now we're going to focus all of our attention tonight on this positive bending region, just like we did last time looking at MP and MY. Although we're going to be looking at the non-composite capacity. Remember when we did MP and MY, we looked at the capacity with the deck on there. Now we're going to be looking at the capacity if that deck was gone, which is incredibly important for later on when we do a deck casting analysis. Make sense? Because the wet concrete has to be supported by the beam itself. Okay. Now what I did not give you last time, but is incredibly important for what we're about to do now, is this. This is the framing plan. Okay? So this tells you how the girders are going to be put together out in the field. Okay? So this bridge has how many beams? 4 beams, right? Okay? So here's beam 1 going longitudinally. Here's beam 2, beam 3, beam 4. Okay? Now, it's probably pretty tough to truck out a beam to a site that's 180 foot long. So what we do is we truck that beam out in pieces and we splice it together. Okay? So this point here and this point here, these black squares are referring to splices. Okay? Some of them might be done in the field, and some of them, if you can fit it on the truck, they might be done in the fab shop. It just depends, okay? But if you notice, your field splices are at the same location that your girder changes sizes, okay? That make sense? All right, so if these are the girders, what are these? Anybody? If these are the girders going this way, what are these things in between them? What's that? Those are the cross frames, right? Remember, I probably have an image, a good picture of it in the last one. All these equations, I think you've earned some pretty pictures. We're talking about these, right? Those cross frames that go in between the girders and brace them from moving laterally, right? So what do we got going on here? Well, let's see where. we've got a cross frame spacing that's 20 feet for most of the bridge, but notice right there around the pier, we threw an additional cross frame in. The cross frame spacing goes to 10 feet. Now, why is it, I mean, think about that logically. Why were there more cross frames around the pier than there were in the main body of the span? Let's think about what's going on at that pier. Well, one of two things are happening. One, at the pier, it's seeing negative bending, right? So think about that. It's seeing negative bending. In the main body of the span, the top flange is in compression. That top flange is right next to that slab. So that slab is taking in a lot of that compression that we don't have to worry about. But over there at the pier, there's no slab, right? The slab's in tension. The compression flange is the flange on the bottom, and it's all by itself, right? So it needs more bracing in order to withstand those loads. That's point one. But point two, the moments themselves are just bigger. We have a lot more bending moment over there at the pier than we do in the main part of the span. Okay? Does that make sense? So we usually, when you're looking at these cross frame layouts, by and large, you probably see more cross frames around the pier than you do in the main body of the span. Does that make sense? Everybody good? Okay. Now, I'm going to show you this Excel sheet, and then we'll take a break. All right? Now, I posted this, so don't worry if you don't follow a lot of this. But a lot of these calcs we've done before, okay? If you recall, get my mouse pointer. If you recall, remember I provided all of these, your dead load and live load moments? And then remember we did all this, right? We distributed them, and then we said, all right, here's our 4 cases, here's what's governing, here's the distribution factor, and there we go, right? Remember that? And then ultimately we got dead load and live load moments that look something like this. Sound good? Now, if you remember, how did we calculate the strength 1 moment? What was it? It was like 1.25 dc plus 1.5 dw plus 1.75 live load plus impact. Remember that? Okay. So this column that you see right here, this is the strength 1 moment. So what am I doing here? Well, I'm taking oh goodness, I forgot a decimal there. Let me throw my decimal in there. Oh, I already took care of that. Oh well, okay. So 1.25, let me go back to the formula. 1.25 times the DC component, so I got DC1 plus DC2, 1.5 times DW, and 1.75 times our live load. And notice how I'm dealing in moments, okay? I'm not dealing in stresses, because you're going to see here in a second that for this girder, Appendix A governs. And if you're in design mode, you want to be designing with Appendix A. Okay, you're going to squeak out more capacity. Sound good? Now, if I plot those moments, it's going to look something about like this. Okay? So let me erase this. This is getting distracting. Whoa. Okay, that's a little strange. There we go. Okay. So here's our strength 1 bending moment. And remember, we're dealing with a range, right? We're not dealing with moment and shear diagrams anymore. We're dealing with moment and shear envelopes. Okay? So here's the beam. Remember, it's 2 90-foot spans. So this is from 0 to 90 and from 90 to 180, something about like that, right? And here's the maximum positive moments. Here's the maximum negative moments. Sound good? Okay. Now, the thing that sucks about this calculation is this right here, okay? Look at this. Okay, remember how we divided the span into 10th points? So we said, if it's a 90-foot span, we'll draw moments, or we'll calculate moments at 9 foot, 8 foot, 18 foot, 27, 36, 45, right? Sound good? The problem is we're going to need moments where those cross frames are, okay? So let's go back to this, all right? So here's our framing plan. We're going to need a moment at x equals 0. But then we're going to need a moment at x equals 20, and at x equals 40, and at x equals 60, and x equals 80. They don't match up, do they, right? So I'm going to have to do some linear interpolation, okay? Take the 2 points and split the difference and say there's the value. That's a lot of linear interpolation to do for this section, and that's a pain in the butt, okay? So I got a little Excel trick that I've given you, okay? Now I'm going to show you what's going on with this Excel trick. All right, so I made up some random data over here. So this is some XY data, okay? It doesn't matter what it looks like, okay? So here's the XY data, and then I've got this blue curve, and that's plotting all that data. So I can go through and change, this to, 8, and it goes through and changes that, okay? What I can do is, based off of this XY data, I can guess some random value of x. Let's say that random value is, 6. Based on that random value, this formula that you see in here, and I know it's a mess, but what this formula does is it figures out, okay, if I'm dealing with 6, which 2 points am I between, and then based on those 2 points, interpolate. It's really slick, okay? And if you are experienced with Excel, you know that having Excel automatically pick those points and having it do that linear interpolation is not something you do on a daily basis. But this is a very nifty trick in Excel. Like if I go through and say, let's make this 4, it automatically knows to go between that second and third point, and there you go. Make sense? So I can make this, 14, and it puts that there. It works with negative values too. Like if I make this, negative 3.68, it knows to interpolate accordingly, and it'll give you a negative value. This is a really slick trick in Excel. And this will help out wonders when we do shear design later. Okay? Does that make sense? This is just useful in general for anything in Excel. When I first saw this trick, I was like, wow, this is pretty cool. So the reason why this is valuable is this. Okay? So here are my strength 1 limit state moments. Okay? I just calculated that from the other sheet. Sound good? All right. So what I've got here is I've got a series of segments. Now I've got 5 segments listed here. And why do I have 5 segments? Well, if I look at the beam and I say, all right, here's the abutment and here's the pier, I've got 1, 2, 3, 4, 5 different beam segments. Sound good? So the first segment's going to go, let's see, from 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 90. Sound good? So here's what I've got. 5 segments, 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 90, right? So for each of these segments, if I just take the difference, this is my unbraced length. 20 for all of these, 10 for the last one. Sound good? Now what's going on in these 3 formulas right here are that same forecasting trick. It's doing a boatload of linear interpolation for me like that. So what I got going on is I do all the linear interpolation for the positive bending one and then the negative bending one, and I just take the worst case scenario that you're going to see here later. So when I do my interpolation, I do 3 values. So for each segment, I figure out the moment at the beginning of the segment, the moment at the end of the segment, and the moment smack dab in the middle. Sound good? So for this segment here, M0 is the moment at 0, M2 is the moment at 20, and then M mid is the moment at 10. Make sense? So I'm just using that same forecasting formula. I know it's a mess, but I'm just copying and pasting and changing my ranges. It's pretty straightforward. Now, I calculate M1. How do I calculate M1? There you go. Pretty straightforward, right? Now, for CB, what I do is this. Anytime that M1 or M2 are 0, CB is 1. Otherwise, this one right here. Okay? Pretty straightforward. Plug and chug. All right. When it's all said and done, I get the following expressions. Now, it's very possible because of the way that CB looks like, it's very possible because of the equation that we use that we get a value less than 1. All right? But I correct that over here. I do the same calculation for all the negative bending regions, and I just take the worst case scenario, and that's it. Okay? So I know this calculation's a little complicated. The reason why it's complicated is just because all the damn linear interpolation you have to do. So I decided to give you a template that you can use for your assignments, because this isn't a computationally tough calculation. It's just Excel. This isn't an Excel class. All right? Sound good? So for any one case, I just take the minimum. So if I'm looking, at this case with 1-to-1, I just take the minimum. From this case, I would take the minimum, but I never take a value smaller than 1. So for these 3 segments, CB would be 1. Now this segment, we have a really large CB value. If you want to think of what CB is, the easiest way to think about it is it's a measure of how much the moment is changing, like how fast it's changing. And this segment that we're talking about here with the 2.3, we're talking about the moment right in here where it's changing a lot, This is a lot of changing in moment, okay? Now, here's the thing, that segment doesn't govern. We don't really care what's going on in that segment. We really mostly care about, from a design standpoint, what's going on here and what's going on there. Sound good? So within that segment, for the positive bending region, we can take CB to be 1. For the negative bending region, we can take it to be 1.38 or 338. And keep in mind, for you all, for your project, you don't even have to deal with negative bending. You just have to find CB at the middle. And more often than not, it's going to be 1. All right. Sound good? Any questions? All right. I've thrown a lot of equations at you. Let's let it soak in. Let's take a break. We're going to come back. We're going to use these equations. And we're going to use these equations on our example, and we're going to compute the capacity. And we're going to go through it so that you all understand what's going on. And when it's all said and done, I think you're going to see this isn't so bad. Everybody good? All right. Let's take a little break. Let's get together in about 10, 15 minutes. What's 7:45? Sound good?